Hello lovelies, in this video we're going to be going over the whole of Eduqas GCSE Geology. Now this is a revision video like all of my others, but it isn't just me, a chemistry teacher, thinking that I can do everything and just getting on with GCSE Geology. We have had this video checked by experts, and if you're a teacher and you know, then you know we have had this checked by the expert. Anyway, to go with this, there is the free revision course over my website with the videos and the questions to really help you revise, to really help you get ready for the exams. We're going to be expanding this and trying to put out as much stuff for you as possible.
Eduqas GCSE Geology. Topic 1. Rocks and minerals. Minerals. Minerals are formed by 1. Crystallization from a melt. Some minerals like quartz, felspar, mica, olivine and augite are formed when a molten rock cools and solidifies. As the temperature decreases, the atoms in the liquid begin to arrange themselves into a regular repeating pattern called a crystal structure. Over time, the crystals grow larger and interlock with each other, forming a solid rock. Number 2. Metamorphic recrystallization. When rocks are subjected to high temperatures and/or pressures, they can undergo metamorphism, a process that can change their mineral composition and texture without the rock melting. During metamorphism, some minerals like calcite can recrystallize, meaning their atoms rearrange into a new crystal structure. These new crystals are often larger and more perfect than the original ones, giving the rock a new appearance and texture. In this way, clay minerals may recrystallize to form garnet. Number 3. Crystallization from solution in evaporating water. Some minerals like halite, rock salt, are formed when water containing dissolved minerals evaporates, leaving behind crystals. As the water evaporates, the concentration of dissolved minerals increases until they reach a saturation point and begin to precipitate out of solution. Over time, the crystals grow larger and can form thick layers of ore deposits called evaporites. Number 4. Crystallization as cement from flowing pore waters. Minerals like quartz and calcite can form as cements that hold sedimentary rocks together. When water flows through sedimentary rocks, it can dissolve minerals and carry them along. As the water evaporates or becomes saturated, the minerals can precipitate out and cement the sediment particles together. This process can create durable rocks like sandstone and limestone. Number 5. Crystallization from hydrothermal fluids. Hydrothermal fluids are hot, mineral-rich fluids that circulate through the Earth's crust. When these fluids meet cooler rocks or open spaces like veins and faults, the minerals can precipitate out and form veins or deposits. Gangue minerals like quartz and calcite are often present in these deposits, while ore minerals like hematite and galena are valuable resources that can be extracted for use in industry. Modern laboratory techniques like scanning electron microscopy, SEM, and electron microprobe analysis can be used to image mineral samples on a small scale and determine their chemistry. Scanning electron microscopy, SEM. SEM is a type of microscope that uses a focused beam of electrons to create images of mineral samples at very high magnifications. Unlike optical microscopes, which use light, SEM can produce images with much higher resolution, allowing scientists to see individual crystals and features on the surface of minerals up to 1 million times the magnification. Electron microprobe analysis. Electron microprobe analysis is a technique that uses an electron beam to determine the elements making up a mineral sample. The microprobe uses a focused beam of electrons to excite the atoms in the sample, causing them to emit characteristic X-rays. By measuring the energy and intensity of these X-rays, the microprobe can determine the type and amount of elements present in the sample. Together, SEM and electron microprobe analysis can provide valuable information about the structure and composition of mineral samples at a very small scale. This information can help geologists understand how minerals form, how they interact with their environment, and how they can be used as resources. Let's now look in depth at igneous rocks. Igneous rocks have diagnostic properties of colour and texture. Number 1, colour. The colour of an igneous rock can provide clues about its composition and the conditions under which it was formed. For example, rocks that are rich in iron and magnesium tend to be dark coloured, while those that are rich in silica tend to be light coloured. Rocks that are shades of green or pink often contain minerals like olivine or feldspar. The colour of an igneous rock can also be affected by weathering or alteration, which can cause it to become discoloured over time. Number 2, texture. The texture of an igneous rock refers to the size and arrangement of its crystals. Different textures can be used to identify the conditions under which the rock formed. For example, crystal size. The size of the crystals in an igneous rock can vary depending on the rate at which it cooled. Rocks that cooled slowly underground tend to have larger crystals than those that cooled quickly at the surface. These coarse-grained rocks with crystals over 3 millimeters are easily visible to the naked eye. Rocks that cooled quickly, on the other hand, tend to have smaller crystals, less than a millimeter, that are difficult to see even with a hand lens. Equicrystalline. If all the crystals in an igneous rock are about the same size, the rock is said to be equicrystalline. This texture can be seen in rocks that cooled at an even rate, such as basalt and peridotite. Porphyritic. Sometimes igneous rocks have 2 distinct crystal sizes. The larger crystals are called phenocrysts, while the smaller ones are called ground mass. Rocks with this texture are called porphyritic. Porphyritic textures can form when magma deep in the crust cools slowly, but is then intruded nearer to the surface to form the finer ground mass, resulting in 2 stages of cooling. Orientation. The orientation of the crystals in an igneous rock can provide clues about how it was formed. Usually, the crystals are randomly orientated, indicating they formed by crystallizing out from a liquid melt. Igneous rocks can be classified by both their texture and mineralogy. Texture refers to the size, shape, and arrangement of the crystals that make up the rock. Mineralogy refers to the types of minerals present in the rock. Let's look at peridotite. The texture is coarse with visible crystals, and its mineralogy is predominantly composed of olivine and augite. Basalt. The texture is fine with small crystals that are often not visible to the naked eye. Its mineralogy is composed of feldspar and augite. Andesite. The texture is medium with visible crystals, and the mineralogy is composed of feldspar, mica, quartz, and augite. Granite. The texture is coarse with large, clearly visible crystals, and its mineralogy is composed of quartz, feldspar, and mica. Overall, the texture of an igneous rock can give us an idea of the cooling rate of the magma or lava from which it formed. Rapid cooling, as in the case of basalt, results in small crystals, while slow cooling, as in the case of granite, results in larger crystals. The mineralogy of an igneous rock can tell us about the composition of the magma or lava from which it formed, as different minerals crystallize at different temperatures and pressures. So, the size of crystals in an igneous rock is related to the cooling rate of the magma from which it formed. The cooling rate affects the rate at which the minerals in the magma crystallize and grow into solid crystals. which then become part of the igneous rock. So to summarise, if magma cools quickly, there is less time for crystals to grow, and so the resulting igneous rock will have smaller crystals. This is because the minerals do not have time to grow large before the magma solidifies. An example of a rock formed from rapidly cooling magma is basalt, which typically has a very fine crystalline or even a glassy texture when erupted as lava at the surface. And on the other hand, if magma cools slowly within the Earth, there is more time for crystals to grow, and so the resulting igneous rock will have larger crystals. This is because the minerals have more time to grow and form larger crystals before the magma solidifies. An example of a rock formed from slowly cooling magma is granite, which typically has a coarse crystalline texture. Therefore, the faster the cooling rate, the smaller the crystal size, and the slower the cooling rate, the larger the crystal size. Magma viscosity is a measure of how easily magma flows when it is erupted onto the surface as lava. It is determined by the composition of the magma, its temperature, and the gas content. Magma viscosity affects the type of volcanic activity and the shape of volcanoes. Relatively passive volcanic activity, such as fissure eruptions, is associated with low viscosity magma. This type of magma is usually basaltic in composition and has a low gas content. Low viscosity magma produces lava at the surface that flows easily, allowing gases to escape, resulting in relatively gentle eruptions. Fissure eruptions occur when lava flows out of long, narrow cracks in the Earth's crust. The lava spreads out in a thin layer and cools to form a broad, flat, plateau-like landform. Examples of fissure eruptions include the Giant's Causeway of the Antrim coast in Northern Ireland, and the picture is below of this. Violent volcanic activity, such as central vent eruptions, is associated with high viscosity magma. This type of magma is usually andesitic or rhyolitic in composition and has a high gas content. High viscosity magma produces lava which is thick and does not flow easily, which causes gas bubbles to become trapped. This can result in explosive eruptions as the pressure of the trapped gases builds up and eventually bursts through the surface. Central vent eruptions occur when lava is ejected from a single central vent in the Earth's crust. The lava is often highly viscous, resulting in explosive eruptions that can send ash and rock fragments high into the atmosphere. Examples of central vent eruptions include the 1980 eruption of Mount St. Helens in the United States. The shape of a volcano is also influenced by magma viscosity. Low viscosity magma typically forms shield volcanoes, which have gentle slopes and broad flat tops. High viscosity magma, on the other hand, typically forms stratovolcanoes, which have steep slopes and a cone-shaped profile. This is because the highly viscous lava does not flow easily and tends to pile up around the vent, forming a steep-sided, cone-shaped structure. Shield volcanoes and composite cones, also known as stratovolcanoes, have different characteristics that can help you distinguish between them based on their size, shape, and composition. Shield volcanoes are generally much larger than composite cones and have a relatively gentle slope. They are formed by the eruption of basaltic lava, which is relatively fluid and tends to flow for long distances before solidifying. This results in a broad shield-like shape that is relatively flat at the top. The lava that forms shield volcanoes is typically low in viscosity, meaning it is relatively easy for the lava to flow out of the volcano. In contrast, composite cones are typically smaller and have a steeper slope. They are formed by the eruption of andesitic or rhyolitic lava, which is more viscous than basaltic lava, and therefore tends to build up around the vent of the volcano, rather than flowing far from it. The result is a tall, cone-shaped volcano with a steep, pointed peak. The layers of ash and lava that form composite cones are typically much thicker than those of shield volcanoes, and the eruptions can be more explosive. Now let's compare Kilauea and Mauna Loa and Mount Pinatubo and Mount St. Helens. Kilauea and Mauna Loa are both shield volcanoes located in Hawaii. They are both characterized by their large size and gentle slopes. Kilauea is the most active of the two, with frequent eruptions that are relatively non-explosive. Mauna Loa, on the other hand, has a longer history of explosive eruptions, although these are relatively rare. Mount Pinatubo and Mount St. Helens, on the other hand, are both composite cones located in the Philippines and the United States, respectively. They are both smaller than Kilauea and Mauna Loa and have steep slopes. Mount Pinatubo erupted in 1991 in a highly explosive eruption that caused significant damage to the surrounding area, while Mount St. Helens erupted in 1980 in a similarly explosive event that was one of the deadliest and most destructive volcanic eruptions in US history. In terms of composition, Kilauea and Mauna Loa are both formed by basaltic lava, while Mount Pinatubo and Mount St. Helens are both formed by andesitic lava. This difference in composition is reflected in the shape and size of the volcanoes, as well as the nature of their eruptions. Igneous bodies can be distinguished by their structure, form, and field relationships. Let's look at structure. Columnar jointing. This refers to the formation of hexagonal columns in igneous rocks due to the contraction of the magma as it cools and solidifies. These columns are often seen in volcanic rocks, such as basalt, and are formed perpendicular to the cooling surface. Pillow lava. This is a type of lava that forms when hot lava erupts underwater or flows into the ocean, causing the outer layer to cool quickly and form a crust. As more pillow lava flows into the crust, it balloons out like a pillow, creating a characteristic pillow-like structure. Now let's look at form, lava flows. These are sheets of molten rock that flow out of a volcano and solidify on the surface. They can be distinguished from other igneous bodies by their thin, flat shape and the fact that they are formed on the surface. They are distinguished by baked margins at their base and often weathered upper surfaces. Sills. These are horizontal sheets of igneous rock that are formed when magma is injected between layers of pre-existing rock and solidifies. They are distinguished from other igneous bodies by their flat shape and their relationship to the surrounding rock layers. Sills show baking of the country rock both above and below. Dikes. These are a sheet-like body of igneous rock that cuts through and across layers of sedimentary rock at an angle to the bedding planes, discordant. They are distinguished by baked margins on both sides of the dike. Plutons. These are large, irregular-shaped bodies of igneous rock that form deep within the Earth's crust and are exposed at the surface through erosion. They can take a variety of shapes, but typically form large dome-shaped bodies that often bake the surrounding rock to form a metamorphic aureole. Now, finally, let's look at field relationships. Igneous bodies can also be distinguished by their relationships to other rocks and geological features in the surrounding area. For example, a sill that cuts across layers of sedimentary rock is likely to be younger than the surrounding rock layers, while a pluton that is exposed at the surface is likely to have cut through the surrounding rock layers. Baked and chilled margins. Baked and chilled margins are features that are formed when a hot intrusion, such as a magma body, comes into contact with cooler country rocks. The difference between the two depends on the degree of thermal alteration that the country rocks undergo. Baked margin is a zone of contact metamorphism that forms in the country rocks surrounding an intrusion. The heat from the intrusion causes the rocks to undergo recrystallization, resulting in changes to the mineralogy and texture of the rocks. Baked margins are characterized by the presence of new minerals, which form because of the higher temperatures. A chilled margin, on the other hand, forms at the edge of the igneous body when the magma cools rapidly against the colder country rocks. Chilled margins are characterized by a fine-grained or even glassy texture that results from rapid cooling. Metamorphic aureoles. Metamorphic aureoles are zones of contact metamorphism that form in the country rocks surrounding an intrusive body. The degree of metamorphism depends on the temperature and pressure conditions created by the intrusion. The width of the metamorphic aureole depends on the size of the intrusive body and the thermal gradient in the surrounding country rocks. The rocks in the metamorphic aureole are altered by the heat and pressure from the intrusion, resulting in changes to the mineralogy and texture of the rocks. The rocks closest to the intrusion undergo the most intense metamorphism, while the rocks further away are less affected. The rocks in the metamorphic aureole can be characterized by the presence of new minerals that formed as a result of the high temperatures. Discordant and concordant relationship. Discordant and concordant relationships refer to the relationship between an igneous body and the surrounding country rocks. A discordant relationship occurs when an intrusive body cuts across the layering or bedding planes of the country rocks. This is usually the result of magma forcing its way into existing cracks and fractures in the rocks. The resulting intrusion is characterized by sharp contacts between the intrusion and the country rocks. A concordant relationship, on the other hand, occurs when the igneous body runs parallel to the layering or bedding planes of the country rocks. This is usually the result of magma following existing weak zones in the rocks, as in a sill, or forming on the surface, as in a lava flow. We now move on to sedimentary rocks. Rock is constantly being broken down by a process known as weathering, which involves the physical and chemical breakdown of rock into smaller particles. Once the rock has been weathered, the resulting particles can be transported and deposited to form new sediments through a process called erosion. There are three main types of weathering: physical weathering, chemical weathering, and biological weathering. Freeze-fall, physical or mechanical weathering. Freeze-fall weathering, also known as frost shattering or ice wedging, is a mechanical weathering process that occurs in an area with a lot of freeze-fall cycles, such as mountainous regions or areas with cold climates. This type of weathering occurs when water seeps into cracks in rocks and then freezes, causing the water to expand and the crack to widen. When the ice melts, it leaves behind a larger crack that can eventually break apart the rock. The repeated freeze-fall cycles can cause rocks to break down into smaller pieces, making them more susceptible to other weathering processes by increasing the surface area that can be weathered. This type of weathering is particularly effective on rocks that have a lot of cracks and fissures, such as granite or limestone. Carbonation or chemical weathering. Carbonation weathering is a chemical weathering process that occurs when rainwater combines with carbon dioxide in the atmosphere to form carbonic acid. When this acid rain comes into contact with rocks that contain calcium carbonate, such as limestone or chalk, it dissolves the rocks over time. The carbonic acid reacts with the calcium carbonate to form calcium bicarbonate, which is soluble in water and can be easily washed away by rain or groundwater. Over time, this can cause a rock to break down and create features such as sinkholes or caves. Action of plant roots, or biological weathering. The action of plant roots is a biological weathering process that occurs when plant roots grow into cracks in rocks and begin to pry them apart. As the roots grow, they can cause the cracks in the rock to widen and break apart. This type of weathering is most effective in areas with a lot of vegetation, such as forests or grasslands. Over time, the roots can break apart the rock and create soil, which allows for even more vegetation to grow. This process is an important part of soil formation and can contribute to the creation of new ecosystems. Once the rock has been weathered, the resulting particles can be transported and deposited through the process of erosion. Erosion is the movement of weathered particles by agents such as water, wind, and ice. For example, when water flows over the surface of the land, it can pick up and transport particles of varying sizes, from fine silt and clay to larger rocks and boulders. As the transported particles are carried along by the erosive agents, they can be sorted by size and deposited in new locations through a process known as sedimentation. Over time, these deposits can accumulate and become compacted and cemented together to form sedimentary rock. The four different types of erosional processes associated with rivers, the sea, ice and wind are abrasion, attrition, hydraulic action, and solution. So firstly, abrasion. Abrasion is an erosional process that occurs when rocks and sediment carried by a river, the sea, ice or wind scrape against the surface of rocks, creating grooves or scratches. In rivers, this process can occur when sediment is carried downstream and rubs against the riverbed or the sides of the river channel. In the sea, abrasion can occur when waves carrying rocks and sediment, which then scrape against the coastline, cause the erosion of cliffs and the formation of beaches. Number 2, attrition. Attrition is an erosional process that occurs when rocks and sediment, carried by a river, the sea, ice or wind, collide with each other, causing them to break into smaller pieces. This process can occur in rivers when rocks and sediment rub against each other as they carry downstream. In the sea, attrition can occur when waves cause rocks and sediment to collide with each other on the beach, causing them to break down into smaller particles. Number 3, hydraulic action. Hydraulic action is an erosional process that occurs when the force of water, ice or wind breaks apart rocks and sediment, creating new pathways for the flow of water, ice or wind. In rivers, this process can occur when fast-moving water hits the riverbed or the sides of the river channel, causing rocks and sediment to break apart. In the sea, hydraulic action can occur when waves hit the coastline, causing rocks and sediment to break apart and erode the coastline. Number 4, solution. Solution is an erosional process that occurs when rocks and sediment are dissolved by a chemical process, such as the action of acid in water. In rivers, this process can occur when the acidity of the water increases due to pollution or natural processes, causing rocks and sediment to dissolve. In the sea, solution can occur when waves bring in water with a higher acidity, causing rocks and sediments to dissolve. The grain size shape and sorting of sediment are influenced by the energy of the transporting medium and the depositional environment. Sediments can be transported by a variety of agents, including water, wind, ice, and gravity, and each of these agents has a different energy level that can affect the size and sorting of the resulting sediment. In general, high energy environments, such as fast-flowing rivers, then deposit their sediments rapidly as the energy levels suddenly drop, which tends to produce sediments with a mixture of grain sizes. This is because the high energy of these environments can move larger particles and keeping them mixed with smaller particles, resulting in a wider range of grain sizes and less sorting. Conversely, low energy environments such as stagnant lakes, quiet river deltas, and deep ocean basins tend to produce sediments with a smaller range of grain sizes and better sorting. In these environments, there is less energy available to move larger particles, so only smaller particles are deposited, resulting in smaller grain sizes and better sorting. The shape of sediment particles can also be influenced by the energy of the transporting medium. In a high energy environment, sediment particles are often angular and poorly sorted when deposited quickly, for example in a flash flood, or rounded and better sorted when transport is for longer or further, e.g. along a pebble beach, and this is due to the constant abrasion and collision between particles. In lower energy environments, sediment particles are typically better rounded and better sorted during transport due to the constant movement of particles. Finally, the depositional environment can also play a role in shaping the sediment. For example, sediments deposited by gravity on a scree slope are typically angular and poorly sorted, while sediments in wind-blown sand dunes are very well rounded and very well sorted. Porosity and permeability are two important properties of sedimentary rocks that depend on the characteristics of the original sediment and the degree of compaction and cementation that occurs during the formation of the rock. Firstly, porosity is a measure of the amount of empty space or voids within a rock or sediment. This is really important because the more porous a rock is, the more water, oil or gas it can store or transmit. The degree of porosity depends on the characteristics of the original sediment that make up the rock, such as its grain size, shape, sorting and packing. A well-sorted sediment with rounded grains and open packing will generally have a higher porosity than a poorly sorted sediment with angular grains and close packing. Permeability is a measure of how easily fluids, such as water or oil, can flow through the rock or sediment. It depends on the size, shape and distribution of the pores, as well as the degree of interconnection between them. For example, sedimentary rocks with high porosity and well-connected pores will generally have high permeability, allowing fluids to flow easily through the rock. During the process of compaction and cementation, sedimentary rocks are compressed and the spaces between the grains are reduced, leading to a decrease in porosity. Cementation involves the deposition of minerals in the pore spaces, which can further reduce the porosity and increase the permeability of the rock. The degree of compaction and cementation depends on factors such as the thickness of the sediment layer, the amount of pressure and temperature the sediment is subjected to, and the nature of the cementing material. Here are some examples of common sedimentary rocks and their diagnostic properties. Number 1, breccia. Breccia is a coarse-grained sedimentary rock that is composed of angular fragments of rocks and minerals. The fragments are typically bound together with a finer-grained material, such as clay or calcite cement. Breccia is often characterized by its sharp, angular edges and its lack of layering. Number 2, conglomerate. Conglomerate is a coarse-grained sedimentary rock that is composed of rounded fragments of rocks and minerals. The fragments are typically bound together with a finer-grained material, such as clay or calcite cement. Conglomerate is often characterized by its well-rounded, smooth-edged pebbles and its lack of layering. Number 3, sandstone. Sandstone is a medium-grained sedimentary rock that is composed of sand-sized grains, which are 1/16 to 2 millimeters, of minerals, rock fragments, or fossils. The grains are typically bound together in a finer-grained matrix, such as clay, or cemented by quartz, calcite, or iron. Sandstone is often characterized by its sandy texture, its layering or bedding, and its ability to produce a gritty feeling when rubbed between the fingers. Number 4, shale. Shale is a fine-grained sedimentary rock that is composed of clay-sized particles. They're less than 1/16 of a millimeter, of minerals, rock fragments, or organic matter. Shale is often characterized by its laminated texture, which results from the layering of fine-grained particles during deposition. Number 5, evaporites. Evaporites are sedimentary rocks that are formed by the precipitation of minerals from evaporating water. Examples of evaporite include rock salt and gypsum. Evaporites are often characterized by their crystalline texture and their ability to dissolve in water. Number 6, limestone. Limestone is a sedimentary rock that is composed mainly of calcium carbonate, which is often derived from the shells of marine organisms and precipitated calcite mud. Limestone is often characterized by its light colour and its ability to fizz when it comes into contact with dilute hydrochloric acid. Here are some examples of the different environments and the types of sedimentary rocks that are typically found in each. Number 1, shallow marine. This environment includes areas like coral reefs, tidal flats, and shallow continental shelves. Limestone is a common rock found in this environment, as well as sandstone and conglomerate. Number 2, deep marine. This environment includes areas like submarine canyons, abyssal plains, and deep sea trenches. Turbidites, which are sedimentary rocks formed from underwater landslides, are commonly found in this environment, as well as black shale. Number 3, terrestrial. Firstly, those that are deposited in rivers and deltas. Sedimentary rocks commonly found in this environment include shale, sandstone, conglomerate, and coal. Rivers and deltas are constantly transporting sediment downstream, which can accumulate and eventually form these types of rocks. Those that are deposited by wind and water in deserts. Sedimentary rocks commonly found in desert environments include breccia and desert sandstone. These rocks are formed from the accumulation of wind-blown sediment or sediment that has been transported by water in temporary streams. Those that are deposited by precipitation from saline water during evaporation. This environment includes areas like salt flats and playas. Evaporites like halite and gypsum are commonly found in this environment, as the saline water evaporates and leaves behind mineral deposits. Deposited by ice. Glacial till, or tillite, is a type of sedimentary rock that forms from the debris and sediment that is transported and deposited by glaciers. Distinctive sedimentary structures such as lamination or bedding, cross bedding, graded bedding, ripple marks, and desiccation cracks are all indicative of the environments in which they were deposited. Number 1, lamination or bedding. This structure is characterized by the layering of sediments in a rock. The thickness, colour and composition of each layer can vary, indicating changes in the sedimentary environment over time. For example, thin, uniform layers of sediment may indicate calm, quiet waters, while thicker, coarser layers may indicate more turbulent conditions. Number 2, cross-bedding. Cross-bedding is created when sediment is deposited at an angle, creating a sloping or angled layer within a larger horizontal layer. The direction of the slope indicates the direction of the current that produced the crossbed. This structure is typically found in environments where sediment is transported by wind or water, such as sand dunes or river channels. Number 3, graded bedding. Graded bedding occurs when sedimentary layers are composed of different sized particles, with the largest particles at the bottom and the smallest at the top. This structure is typically formed in environments where sediment is deposited quickly, such as during a flood or turbidity current. Number 4, ripple marks. Ripple marks are small, wave-like ridges that form on the surface of sedimentary layers. They are typically found in environments with shallow water or wind-blown sediment, such as lakes, beaches, or desert dunes. Number 5, desiccation cracks. Desiccation cracks are formed when mud or clay dries out and contracts, creating polygonal patterns of cracks. These cracks are typically found in environments with a dry, arid climate, or in areas that experience periodic droughts. Fossils are the remains or traces of ancient organisms that have been preserved in rocks. Here's how different types of fossils can indicate past environments. Number 1, reef-building corals. These fossils are typical of a tropical marine environment that was shallow and warm. Reef-building corals require clear, so sediment-free, warm water, 22 to 28 degrees Celsius, with a steady supply of calcium carbonate to form the structures that make up coral reefs. Therefore, their presence in sedimentary rocks suggests that the rocks were formed in a shallow marine environment with warm water. Number 2, trilobites and ammonites. These fossils are also indicative of a marine environment. Trilobites were marine arthropods that lived during the Paleozoic era, while ammonites were shelled cephalopods that lived during the Mesozoic era. The presence of these fossils in sedimentary rocks indicates that the rocks were formed in a marine environment, possibly in a shallow or deep sea. Number 3, plants. Fossilized plants can provide clues about past terrestrial environments, including the climate and vegetation. For example, the presence of fossils of tropical plants in sedimentary rocks suggests that the rocks were formed in a warm, humid climate. The absence of certain types of plants in sedimentary rocks can also indicate changes in climate or environmental conditions over time. Number 4, trace fossils. These fossils are not the remains of organisms themselves, but rather evidence of their activity. For example, tracks left by animals on land indicate a terrestrial environment, while burrows left by marine animals suggest a shallow water environment. Trace fossils can also provide information about the behaviour and ecology of ancient organisms, such as their feeding habits and modes of locomotion. By studying fossils, geologists can reconstruct past ecosystems and gain a better understanding of how the Earth has changed over time. We now move on to metamorphic rocks. Metamorphic rocks are formed when pre-existing rocks are subjected to increased temperatures and/or pressure. The combination of these factors causes the minerals to recrystallize without melting, forming new minerals and textures. Here's a brief explanation of the processes involved in the formation of metamorphic rocks. Number 1, heat. Increased temperature is one of the main agents of metamorphism. When rocks are subjected to high temperatures, the minerals within them become unstable and may start to break down. Over time, these minerals may recombine to form new minerals with different chemical compositions and crystal structures. Number 2, pressure. Increased pressure is another agent of metamorphism. When rocks are subjected to high pressure, their grains may become tightly packed together, causing recrystallization to occur. The direction of the pressure may also cause new minerals to grow in a specific pattern, creating new textures such as foliation. Number 3, fluids. Fluids such as water or other fluids can also play a role in metamorphism. Fluids can help to transport ions between minerals, causing chemical reactions and new mineral growth. They can also contribute to the removal or addition of elements from the rock, changing its composition. The type of metamorphic rock that forms depends on the degree of heat and pressure applied, as well as other factors such as the presence of fluids. Metamorphic rocks can have diagnostic textures that provide clues about their formation and the conditions they experience during metamorphism. Number 1, contact metamorphism. Contact metamorphism occurs when rocks are heated due to contact with magma or lava. When hot magma or lava comes into contact with cooler rocks, it can transfer heat to the surrounding rocks, causing them to be heated and undergo contact metamorphism. The heat causes the minerals in the rock to recrystallize, forming new minerals and changing the texture and structure of the rock. This process can also cause the rock to become harder and more resistant to weathering and erosion. Contact metamorphism typically occurs in areas where there are igneous intrusions, such as around the edges of plutons or along the contact between lava flows and sedimentary rocks. Number 2, regional metamorphism. Regional metamorphism occurs when rocks are subjected to high pressure and temperature over a large area, often due to tectonic activity. This process can occur when two tectonic plates collide, causing rocks to be squeezed and deformed. The pressure causes the minerals in the rock to recrystallize, once again forming new minerals and changing the texture and structure of the rock. The temperature also plays a role, as it can cause chemical reactions to occur between the minerals in the rock. Regional metamorphism typically occurs in areas where there is mountain building activity, such as at convergent plate boundaries where two tectonic plates collide. In summary, contact metamorphism occurs when rocks are heated due to contact with magma or lava, while regional metamorphism occurs when rocks are subjected to high pressure and temperature over a large area due to tectonic activity. Both processes cause the minerals in the rock to recrystallize and form new minerals, changing the texture and structure of the rock. Let's look at textures. Number 1, a non-foliated texture. This texture is found in metamorphic rocks that do not show a parallel arrangement of minerals known as foliation. Non-foliated rocks may have a fine-grained texture with small crystals or a coarse-grained texture with larger crystals. Marble, which forms from the contact metamorphism of limestone, is an example of a non-foliated rock. Marble typically has a fine-grained, equicrystalline texture with small crystals of calcite. Metaquartzite forms from the contact metamorphism of quartz sandstone that typically has a fine to medium-grained, sugary texture. It is characterized by interlocking quartz grains that are well cemented and have recrystallized to form a hard, dense rock. Number 2, a foliated texture. This texture is found in metamorphic rocks that have a parallel arrangement of minerals known as foliation. Foliation is caused by the alignment of minerals in response to directed pressure, which influences crystal growth during metamorphism. There are different types of foliation textures, including slaty cleavage. This is a smooth, flat surface that develops in fine-grained, clay-rich rocks, such as shale or mudstone. During metamorphism, the minerals in the rock become aligned along cleavage planes, resulting in a parallel arrangement of platy minerals that are perpendicular to the direction of pressure. Slaty cleavage is commonly found in rocks that have been metamorphosed under low to moderate pressure and temperature conditions, such as slate. Schistosity. This texture is characterized by a coarser-grained, platy or elongated mineral arrangement, with minerals such as mica aligned perpendicular to the direction of pressure. Schistosity develops in rocks that have been subjected to higher pressure and temperature conditions than those that form slaty cleavage. The resulting minerals in the rocks are larger and more visible, giving the rock a distinctive striped appearance. Schist is an example of a rock with a texture called a schistosity. Gneissic banding. This texture is characterized by alternating bands of light and dark minerals with a coarser texture than schist. Gneissic banding develops in rocks that have been subjected to high pressure and temperature conditions, resulting in the segregation of minerals into light and dark mineral bands. Gneiss is an example of a rock with gneissic banding. Some metamorphic rocks can be the product of both contact and regional metamorphism, as in the case of marble and metaquartzite. Metamorphic rocks, such as schist, marble, and metaquartzite, have diagnostic mineralogy that can be used to identify them. Schist is a metamorphic rock that is characterized by its visible parallel layered structure called foliation. The minerals that make up schist are typically micas such as biotite and muscovite, as well as minerals such as quartz and feldspar. These minerals give schist its characteristic shiny reflective appearance and its ability to split into thin, wavy layers. And this picture is of a quartz schist. Marble, on the other hand, is a metamorphic rock that is composed primarily of calcite. Marble is formed from the metamorphism of limestone, which is a sedimentary rock composed of calcium carbonate. Marble has a characteristic white or light-coloured appearance and will effervesce with dilute hydrochloric acid, giving off carbon dioxide gas. Metaquartzite is a metamorphic rock that is composed of primarily quartz. Quartz is a hard, durable mineral that is resistant to weathering and erosion, which gives metaquartzite its characteristic durability and hardness. Metaquartzite is typically light-coloured, has a crystalline appearance, and does not effervesce with dilute hydrochloric acid. We now look at deformational structures. The rock record, which is a collection of all the rocks that have formed over time, provides us with valuable evidence of past tectonic activity. Firstly, the rock types. The type of rock that is present in an area can provide evidence of the tectonic activity. For example, igneous rocks like granite and basalt are formed through volcanic activity, which is often associated with tectonic plate boundaries. Sedimentary rocks are usually laid down horizontally, but later deformed by tectonic activity, which has pushed the land up and exposed the rocks to weathering and erosion. Secondly, fossils. Fossils are the remains of plants and animals that lived in the past and are preserved in rocks. The distribution of fossils in rock layers can provide evidence of tectonic activity. For example, if the same type of fossil is found in rock layers on opposite sides of a plate boundary, it suggests that the plates were once connected and have since moved apart. Thirdly, folded and faulted rocks. Rocks that have been folded or faulted can provide evidence of tectonic activity. Folding occurs when rocks are subjected to pressure and deformation, and the amount of which can be assessed by measuring the dip and strike of the beds. Folding occurs when rocks are broken and displaced along a fault line, which is also a result of tectonic movement. Fourthly, volcanic activity. Volcanic rocks, like lava and ash, can provide direct evidence of tectonic activity. The location and age of volcanic rocks can provide information about the location and timing of tectonic activity. Folding is a type of deformation in rocks that occurs when tectonic stresses cause the rocks to bend and buckle. This type of deformation is common in areas where compressional tectonic forces are at work, such as at convergent plate boundaries. When two tectonic plates collide, they can create compressional stress that pushes the rocks together. This stress causes the rocks to deform, with the layers of rock bending and folding. The rocks in the middle of the fold experience the most compression and are squeezed together, while the rocks on the outside of the fold experience tension and are pulled apart. The shape and size of the folds depends on the intensity and direction of the tectonic forces, as well as the strength and composition of the rocks. Antiforms, shown on the picture on the left, are folds in which the limbs arch upwards and dip away from each other, while synforms, the picture on the right, folds downwards in a U-shape with limbs that dip towards each other. Folding can have a significant impact on the landscape, creating mountains, valleys, and other distinctive landforms. It can also affect the distribution and quality of natural resources, such as oil and gas, as they tend to accumulate in areas of folded rock. Faulting is a type of geological process that occurs when tectonic stresses cause rocks to break and move along a fracture in the Earth's crust. Faults are classified based on the type of tectonic stress that caused the rocks to break and move. Compressional stress. When two tectonic plates converge, they can create compressional stress that pushes the rocks together. This stress can cause the rocks to break and move along a fault in a process called reverse faulting. Reverse faults are characterized by a hanging wall above the fault plane that moves upward relative to a footwall below the fault plane. Thrust faults are a type of reverse fault where the angle of dip of the fault plane is low, often less than 20 degrees from the horizontal. This type of faulting often leads to the formation of mountains and is common at convergent plate boundaries. Tensional stress. When two tectonic plates diverge, they can create tensional stress that pulls the rocks apart. This stress can cause the rocks to break and move along a steeply dipping fault in a process called normal faulting. Normal faults are characterized by a hanging wall that moves downward relative to a footwall. This type of faulting is common at divergent plate boundaries, such as mid-ocean ridges. Shear stress. When two tectonic plates slide past each other, they can create shear stress that causes the rocks to break and move along a fault in a process called strike-slip faulting. Strike-slip faults are characterized by rocks that move horizontally past each other. This type of faulting is common at transform plate boundaries, such as the San Andreas Fault in California. Fault displacement is measured by the amount of relative movement that has occurred along a fault plane, and is calculated by measuring the displacement of the same bed on either side of a fault. In geology, an unconformity refers to a break or gap in the rock record that represents a period of time during which no rock was deposited or preserved. In other words, an unconformity is a missing part of the geological history. There are several types of unconformities, but one common type is an angular unconformity. This type of unconformity is formed by a sequence of events that includes deformation, uplift, erosion, and later deposition. Here's how it works. Let's say that a sequence of sedimentary rocks is deposited horizontally over a long period of time. Then, at some point in the geological past, tectonic forces causes the rocks to become deformed, tilting them at an angle. This deformation can be caused by processes such as mountain building or plate tectonics. After the rocks are tilted, they are exposed to erosion. Over time, weathering and erosion wear away the uppermost layers of rock, eventually exposing the older, tilted layers below. This creates a gap in the rock record, where the time between the deposition of the horizontal sedimentary rocks and the erosion of the tilted rocks is not recorded. Finally, after the erosion has taken place, new sedimentary rocks are deposited on top of the eroded surface. These new rocks can be deposited in a horizontal orientation, which creates an angular unconformity between the older tilted rocks and the younger horizontal rocks. Eduqas GCSE Geology. Topic 2, Earth and its history. The rock cycle. The rock cycle is a fundamental concept in geology that explains how rocks are transformed from one type to another over geological time. The three main types of rock are sedimentary, metamorphic, and igneous, and they are linked by the rock cycle through a process of energy transfer. Sedimentary rocks are formed by the accumulation and compaction of sediment, which can be derived from the weathering and erosion of existing rocks, or from the deposition of organic matter. Sedimentary rocks are formed by the accumulation and cementation of sediment that has been transported by water, wind, or ice. Sedimentary processes are controlled by the hydrological cycle, which is a continuous circulation of water between the Earth's surface and the atmosphere. Water is a major agent of sediment transport and erosion, and sediment is often deposited in rivers, lakes, and oceans. Sediments that can accumulate over time can be compressed and cemented together to form sedimentary rocks. The energy sources that drives the formation of sedimentary rocks is primarily the energy of the sun, which provides the heat and energy necessary for weathering and erosion to occur, and gravity. As rocks are buried under the Earth's surface, they are subjected to increase in pressure and temperature, which leads to their transformation into metamorphic rocks. Metamorphic rocks are formed by the recrystallization of existing rocks under high pressure and/or temperature conditions. The energy source that drives the formation of metamorphic rocks is primarily the Earth's internal heat, which is generated by the decay of radioactive elements. Finally, as rocks are subjected to even higher temperatures, they can melt and solidify to form igneous rocks. Igneous rocks are formed by the cooling and solidification of magma or lava. The energy source that drives the formation of igneous rocks is also the Earth's internal heat, which drives the melting of existing rocks. Once formed, igneous rocks can be weathered and eroded to form sediment, which can then be deposited and compacted to form new sedimentary rocks, thus completing the rock cycle. The energy from the sun and also gravity drives the formation of sedimentary rocks, while the Earth's internal heat drives the formation of metamorphic and igneous rocks. Let's discuss the importance of gravity in the rock cycle. Gravity is an important force in the rock cycle as it plays a key role in the movement of sediment and the transportation of rocks. Sediment is transported by water, wind, and ice, and gravity helps to move sediment down slopes and towards areas of lower elevation. Gravity is also important in the formation of sedimentary rocks, as the weight of overlying sediment can cause the compaction and cementation of sediment into rock. Additionally, gravity can cause rocks to be eroded and transported during mass wasting events, such as landslides and rockfalls. The rock cycle is a continuous process that involves the transformation of rocks from one type to another over geological time. These processes can take place at different rates, ranging from seconds to millions of years, and they can be broadly classified into two categories: catastrophism and gradualism. Catastrophism refers to the rapid and dramatic changes in the Earth's surface caused by catastrophic events, such as meteorite impacts or volcanic eruptions. These events can result in the sudden formation of new rocks or the destruction of existing ones. For example, a meteorite impact can create a large crater and generate shock waves that cause rocks to melt and solidify into new forms. Similarly, a volcanic eruption can release large quantities of lava, which can rapidly cool and solidify into new igneous rocks. In contrast, gradualism refers to the slow and steady processes that shape the Earth's surface over long periods of time, such as erosion, weathering, and sedimentation. These processes can take millions of years to transform rocks from one type to another. For example, the erosion of a river can slowly wear away at the surface of rocks and carry sediment downstream, which can eventually be deposited and compacted to form new sedimentary rocks. Similarly, the slow movement of tectonic plates can gradually push rocks deep into the Earth's mantle, where they can be transformed into new forms through heat and pressure. It's important to note that both catastrophism and gradualism are important in shaping the Earth's surface and driving the rock cycle. Catastrophic events can create sudden changes that can have a profound impact on the landscape, while gradual processes can shape the landscape over long periods of time. Moreover, both types of processes can interact with each other, as catastrophic events can set in motion gradual processes that continue long after the initial event has occurred. Let's take an in-depth look at plate tectonics. The Earth has a concentric structure, with distinct layers based on its chemical properties and mechanical behaviour. The chemical properties. The Earth's concentric structure is primarily based on its chemical properties, which are determined by the different elements that make up the planet. Three main layers are the crust, mantle, and core. Firstly, let's look at the crust. The Earth's crust is the outermost layer and is composed of primarily silicate rocks. It is relatively thin, averaging around 35 kilometres in depth beneath continents, and roughly 7 to 10 kilometres in depth beneath oceans. The crust can be divided into two types: continental crust, which is thicker and less dense, and oceanic crust, which is thinner and more dense. Secondly, the mantle. The mantle is the solid layer beneath the crust and extends to a depth of around 2,900 kilometres. It is composed of silicate rocks that are rich in iron and magnesium, and it is also divided into two parts: the upper mantle and the lower mantle. Finally, the core. At the centre of the Earth is the core, which is composed primarily of iron and nickel. It is divided into two parts: the outer core and the inner core. The outer core is liquid, while the inner core is solid. Mechanical behaviour. In addition to the chemical properties, the Earth's structure can also be classified based on its mechanical behaviour. In this way, the outer part of the Earth can be divided into two layers: the lithosphere and the asthenosphere. Firstly, let's look at the lithosphere. The lithosphere is the cold, rigid outer layer of the Earth that includes the crust and the uppermost part of the mantle. It behaves mechanically like a rigid outer shell and is broken up into tectonic plates that move and interact with one another. Secondly, the asthenosphere. The asthenosphere is a hot, weak layer of the mantle that lies beneath the lithosphere and is capable of deforming slowly by flowing as a solid over geological timescales. It behaves mechanically like a weak solid, with the lithospheric plates moving above, driven by processes which are not yet fully understood, but thought to possibly involve slab pull and ridge push. The lithosphere and the asthenosphere interact with each other in important ways that drive the geological processes that shape our planet. The movement of the lithosphere plates can cause earthquakes, volcanic eruptions, and the formation of mountain ranges. As the plates move, they can interact with each other in various ways, such as colliding, spreading apart, or sliding past each other. These interactions can lead to the formation of features such as mid-ocean ridges, subduction zones, and transform faults. The movement of these plates is driven by forces within the Earth, but the mechanisms underlying plate movement are not yet completely understood. There are currently 7 major tectonic plates and several smaller plates that make up the lithosphere. These plates are described as either continental or oceanic plates, depending upon the type of crust involved. Tectonic plates are defined by their boundaries, which can be divergent, meaning moving apart, convergent, moving towards each other, or transform, which means they slide past each other. The movement of tectonic plates was once thought to be driven by convection in the underlying mantle, but this is no longer considered to be an important mechanism. However, the exact mechanisms underlying plate movement are still a subject of ongoing research and debate among geologists. Plate movement has important geological consequences, such as the formation of mountain ranges, earthquakes, and volcanic activity. At divergent plate boundaries, new crust is formed as magma rises to the surface and solidifies, creating mid-ocean ridges. At convergent plate boundaries, one plate is typically forced beneath another in a process known as subduction, which can cause earthquakes and volcanic activity. Transform plate boundaries are characterized by horizontal movement, which can also cause earthquakes. There are several possible drivers of plate movement. The first is slab pull. Slab pull is one of the main forces that drives plate motion, particularly the movement of subducting plates at convergent plate boundaries. This process occurs as a dense oceanic lithosphere at the leading edge of the subducting plate sinks into the mantle. As the lithosphere sinks, it pulls the rest of the plate behind it, creating a pulling force that helps to drive plate motion. Secondly, ridge push. Ridge push is another force that drives plate motion, particularly at mid-ocean ridges where new oceanic crust is created. This process occurs as the newly formed oceanic lithosphere at the ridge crest is pushed by the upwelling of hot mantle material beneath the ridge. The higher elevation causes the plate to slide away from the ridge axis by gravitational forces. This creates a pushing force that helps to drive plate motion away from the ridge. Thirdly, mantle drag. Mantle drag is a frictional force whereby convection currents in the asthenosphere were once thought to drag the overlying plate to contribute to plate motion, particularly at divergent plate boundaries. There is little evidence for this process, and it is now not considered to be an important mechanism, although we still widely see it referred to in textbooks. Fourthly, slab suction. Slab suction is a force that is thought to contribute to plate motion. particularly at subduction zones where one plate is forced beneath another. This process occurs as the sink in lithosphere creates a low pressure region in the mantle beneath the subduction zone. This low pressure region can create a suction force that helps to pull the plate down into the mantle. The mechanisms underlying plate movement are not yet completely understood, but are now thought to be an important part of the overall convection processes within the whole Earth. Plate movement has important geological consequences and can lead to the formation of features such as mountain ranges, earthquakes, and volcanic activity. The theory of plate tectonics is the current model used by geologists to explain the movement of the Earth's lithospheric plates. This theory is developed from the earlier theory of continental drift, which was first proposed by Alfred Wegener in 1915. Wegener suggested that the continents were once joined together in a single landmass called Pangaea, which later broke apart and drifted to their current positions. He used the jigsaw pattern fit of the continents and the distribution of rocks and fossils as evidence. Although his ideas were initially met with skepticism, further research and the discovery of new evidence supported the idea of continental drift. In the 1960s, new evidence was discovered that helped to support the theory of plate tectonics. This evidence came from studies of the age and structure of the ocean floor, which showed that the seafloor was not a flat plain, but rather had ridges, valleys, and mountain chains that were younger near the centre. Harry Hess proposed the idea of seafloor spreading in 1960, which suggested that new crust was being formed at mid-ocean ridges and spreading away from the ridge axis. This idea was supported by the discovery of magnetic stripes on the seafloor by Vine and Matthews in 1963, which showed that the Earth's magnetic field had reversed multiple times in the past. These magnetic stripes were symmetrically arranged around mid-ocean ridges, providing evidence for the creation of new crust at these locations. J. Tuzo Wilson further developed the theory of plate tectonics by proposing that the Earth's lithosphere was broken up into several plates that moved relative to one another. This movement was later confirmed by Global Positioning System (GPS) data. Firstly, one of the key pieces of evidence for plate tectonics is the distribution of earthquakes and volcanoes around the world. These events tend to occur along plate boundaries, where the movement of plates causes stress and pressure to build up, leading to earthquakes and volcanic eruptions. Secondly, the magnetic striping on the ocean floor provides strong evidence for plate tectonics. As molten rock rises to the surface at mid-ocean ridges, it cools and solidifies, creating new sections of oceanic crust. This process also locks in the orientation of the Earth's magnetic field at that time. By studying the magnetic properties of the rocks on either side of the mid-ocean ridge, scientists can determine the age of the crust and the direction and rate of plate movement. Thirdly, the fossil record also supports the theory of plate tectonics. When plates move, they can cause land masses to separate or collide, creating new environments for plants and animals. By studying the distribution of fossils across different continents, scientists can piece together the history of plate movements and the evolution of life on Earth. Lastly, geophysical techniques such as GPS and satellite measurements allow us to directly measure the movement of plates and the deformation of the Earth's surface. These data confirms the direction and rate of plate movements, which is consistent with the predictions of plate tectonics theory. Recently, seismic tomography has helped to reveal the deep structure of the mantle with evidence of subducted oceanic lithosphere at depths of greater than 2,000 kilometers. Ocean drilling has also discovered asymmetrical spreading along parts of divergent margins, with mantle peridotite exposed on the seabed, now altered to serpentinite, as part of ocean core complexes. These pieces of evidence all point to the same conclusion, that the Earth's lithosphere is divided into large plates that move and interact with each other, shaping the surface of our planet over millions of years. The movement of tectonic plates relative to one another can produce a variety of geological features and processes that vary depending on the type of plate boundary. There are three types of plate boundaries: divergent, convergent, and transform or conservative. At divergent plate boundaries, plates move apart from each other. This creates gaps in the crust through which molten magma from the mantle can rise up and solidify, forming new oceanic crust. The magma produced at divergent plate boundaries is typically basaltic in composition, and it is derived from partial melting of the upper mantle. This can result in seafloor spreading, ocean ridges, high heat flow, and rift valleys. A good example of this is the Mid-Atlantic Ridge. At conservative or transform plate boundaries, plates slide past each other horizontally. This creates earthquake activity and is marked by transform faults. The most well-known example of a conservative plate boundary is the San Andreas Fault in California. At convergent plate boundaries, two plates move towards each other, and these can result in three types of boundaries depending on the type of plate collision: oceanic to oceanic, oceanic to continental, or continental to continental. At oceanic to oceanic convergent plate boundaries, the denser of the two plates will subduct beneath the other, creating a deep oceanic trench. The subducting plate will release water, held within the structure of the minerals, into the mantle. This causes partial melting of the overlying mantle wedge, the melts from which rise and form magma reservoirs in the crust above. As the magma rises to the surface, it can produce volcanoes that form island arc trench systems, such as those found in Java, Sumatra, or the Caribbean. At oceanic continental convergent plate boundaries, the oceanic plate will subduct beneath the continental plate, creating an active continental margin. The subducting oceanic plate will release water into the mantle, causing partial melting of the overlying mantle wedge, which evolves into andesitic and granitic magmas in the overlying crust. These magmas can rise to the surface and produce volcanic mountain ranges such as the Andes. At continental to continental convergent plate boundaries, two continental plates will collide, resulting in mountain building, folding, and thrust faulting. The immense pressure and heat generated by the collision can cause partial melting of the continental crust, producing granitic magmas. The process of continental collision is often associated with regional metamorphism, as rocks are altered and deformed by the intense pressures and temperatures. The Himalayas are a well-known example of a mountain range that formed as a result of continental collision. Plate tectonic theory is not a static idea and is continually re-evaluated as new evidence emerges. For example, advancements in technology such as seismic tomography and ocean drilling have led to new insights into the structure and behaviour of the Earth's lithosphere and mantle. Seismic tomography is a technique that uses the velocity of seismic waves to create images of the Earth's interior. By analysing the speed and direction of seismic waves, scientists can create three-dimensional models of the Earth's structure, including the location and movement of tectonic plates. This technique has allowed scientists to better understand the complex interactions between tectonic plates and the underlying mantle. Ocean drilling is another important tool for investigating plate tectonic theory. the RRS James Cook, and the JOIDES Resolution are research vessels that are used for drilling deep beneath the ocean floor to collect rock and sediment samples. These samples can provide valuable information about the history of plate movement, the evolution of ocean basins, and the formation of mountain ranges. In 2016, the JOIDES Resolution completed Expedition 360, which focused on drilling in the Indian Ocean to investigate the tectonic history of the region. The samples collected during this expedition helped to shed new light on the evolution of the Indian Ocean and the role of plate tectonics in its formation. We'll now look at geochronological principles. Geological events are dated and interpreted using stratigraphic principles, which are based on the observation and interpretation of rock layers, or strata, and their relationships to each other. The main principles of stratigraphy that are used for this purpose are uniformitarianism, original horizontality, lateral continuity, superposition, including fragments and cross-cutting relationships, along with the use of fossils. Uniformitarianism is the principle that states that the processes that operate today to shape the Earth's surface have been in operation throughout geological time. This means that the present is the key to the past, and that geologists can use observation of present-day processes to understand past geological events. The concept of original horizontality states that sedimentary rocks are deposited in horizontal layers. This principle is based on the observation that sedimentary rocks often have flat, parallel layers that have not been disturbed since they were deposited. Lateral continuity is the principle that states that sedimentary rocks are deposited over large areas and are later eroded or deformed into smaller, isolated outcrops. This means that layers of rock that are now separated by valleys or other features were once continuous and can be correlated across a larger area. Superposition is the principle that states that, in an undisturbed sequence of sedimentary rocks, the oldest rocks are at the bottom and the youngest rocks are at the top. This principle is based on the observation that new sedimentary layers are deposited on top of older layers. Using these principles, geologists can determine the relative ages of different rock layers. For example, if a layer of rock contains fragments of another older rock layer, then the layer containing the fragments must be younger than the layer from which the fragments were derived. Similarly, if a layer of rock cuts across another layer, then the layer that is cut must be older than the layer that cuts across it. Rocks can be dated and correlated using the evolutionary change in zone fossils over time. Fossils are the remains or traces of organisms that lived in the past, and they can provide important clues about the age and characteristics of the rocks in which they are found. One way that geologists use fossils to date rocks is by looking at the evolutionary history of organisms. Different types of organisms have evolved over time, and their fossils can be used to create a timeline of the history of life on Earth. Geologists use this timeline to assign relative ages to different rocks. Zone fossils are fossils that are used to define a specific interval of geologic time. They are often used to correlate rocks from different regions or to date rocks that are not directly dated by other methods. Zone fossils are typically organisms that evolved rapidly and had a wide geographic distribution, such as cephalopods and graptolites. Geologists can use zone fossils to create biostratigraphic zones, which are intervals of geologic time characterized by a specific group of fossils. By identifying these zones in different rocks, geologists can correlate the rocks and determine their relative ages. For example, if a certain species of graptolite is found in a rock layer in one region and in a different layer in another region, then geologists can infer that the two rock layers are the same age. Graptolites are a type of extinct marine animal that lived during the Lower Paleozoic era, which spanned from about 540 to 400 million years ago. These animals were colonial, meaning that they lived in groups or colonies, and they were planktonic, meaning that they drifted in the water column. Graptolites left behind a rich fossil record, and their fossils can be used to help date and correlate rock formations from this time period. They had a simple, tube-like structure and lived in colonies. The stipes, branches, and theca, the cups that house the animals, show a range of morphological changes over time. The number and orientation of the stipes change from many, which face down, to just one, facing upwards. In addition, there was a change in the number, position, and increased complexity of the thecae over time. Geologists use these changes to identify different species and create biostratigraphic zones. They evolved rapidly and had a wide geographic distribution. Graptolites are particularly useful for zonal classification of lower Paleozoic rocks because different species of graptolites lived during different periods of this era. By studying the distribution of different graptolite species in rock formations, geologists can create a biostratigraphic zonation scheme that can help to correlate rocks from different regions. Cephalopods, on the other hand, are a diverse group of marine animals that include goniatites, ceratites, and ammonites. These animals lived during the Upper Paleozoic and Mesozoic eras, which spanned from about 400 to 66 million years ago. Cephalopod fossils are particularly useful for zonal classification of rocks from these time periods because they evolved rapidly and left behind a diverse fossil record. Cephalopods are marine animals that have a hard, coiled shell. They have existed for hundreds of millions of years, and different species have evolved at different times throughout Earth's history. The suture line, which is the line where the shell is divided into chambers, is used to identify and distinguish different species. Over time, the shape of these suture lines, where the internal walls of their body chambers meet the outer edge of the shell, changes from simple, in the Carboniferous, to more complex, in the Cretaceous. Cephalopod fossils are particularly useful for zonal classification of rocks from these time periods because they evolved rapidly and left behind a diverse fossil record. By studying the distribution of different cephalopod species in rock formations, geologists can create a biostratigraphic zonation scheme that can help to correlate rocks from different regions. By examining the fossil record and identifying zone fossils, geologists can create a timeline of the history of life on Earth and use it to determine the relative ages of different rocks. The decay of radioactive materials provides a method of absolute dating for some rocks and minerals. This method is called radiometric or absolute dating, and it relies on the fact that radioactive isotopes decay at a constant rate over time. Radioactive isotopes are unstable atoms that decay into more stable forms over time by emitting particles or energy. The rate at which this decay occurs is measured in half-lives, which is the time it takes for half of the original material to decay. By measuring the ratio of the radioactive parent isotopes to the stable daughter isotopes in a rock or mineral, geologists can determine how many half-lives have elapsed since the rock or mineral formed. There are several radioactive isotopes that are commonly used for radiometric dating. For example, uranium-238 decays into lead-206, and the half-life of this decay is 4.5 billion years. This means that if a rock or mineral contains uranium-238 and lead-206, the ratio of the two isotopes can be used to determine the age of the rock or mineral. Other isotopes that are commonly used for radiometric dating include potassium-40, carbon-14, and rubidium-87. Radiometric dating is a powerful tool for geologists because it can provide absolute ages for rocks and minerals. This information is critical for understanding the geologic history of the Earth, including the timing of major events such as the formation of continents and the extinction of species. However, radiometric dating is not always reliable, as there are many factors that can affect the accuracy of the results. These factors include contamination, loss or gain of isotopes, and changes in the rate of decay over time. Geologists must carefully evaluate these factors and use multiple methods of dating to ensure the accuracy of their results. The development of the concept of deep time has been a significant milestone in our understanding of the age of the Earth. Deep time refers to the idea that the Earth's history is much longer than previously thought, and that the processes that shape the Earth have been happening for millions and billions of years. Before the development of deep time, people believed that the Earth was only a few thousand years old, based on religious and biblical accounts. Archbishop James Ussher, in 1650, for example, calculated the age of the Earth to be 6,000 years, based on the genealogies described in the Bible. However, in the 18th and 19th centuries, scientists such as James Hutton, Lord Kelvin, John Joly, and Arthur Holmes developed new theories and methods for determining the age of the Earth that challenged these beliefs. Hutton proposed the idea of uniformitarianism, which suggests that geological processes that shape the Earth are gradual and occur over long periods of time. Kelvin used the rate of cooling of the Earth to estimate its age, while Joly used the rate of salt build-up in the oceans. Holmes developed the concept of radiometric dating, which allows scientists to calculate the age of rocks and minerals based on their radioactive decay. These scientists, among others, contributed to the development of the concept of deep time, which has extended the age of the Earth back to around 4.6 billion years. This estimate is based on a variety of methods, including radiometric dating of rocks and minerals, the study of fossils and their distribution, and the observation of geological processes such as erosion and volcanic activity. Global climate and sea level change. There is evidence for global climate change through geological time, which is reflected in the rock record. Geological evidence can provide insights into the climate conditions that existed on Earth millions of years ago, and how they have changed over time from cooler icehouse to warmer greenhouse conditions. Two examples of geological evidence for global climate change are the deposition of glacial deposits in regions close to the equator and the deposition of limestone in areas outside the tropics. During the Carboniferous period, which occurred around 300 million years ago, the Earth experienced a period of global cooling that led to the formation of glaciers in regions close to the equator. This is evidenced by the presence of glacial deposits, known as tillites, in places such as Africa and South America, which were located near the equator at the time. These tillites contain sedimentary structures that are indicative of glacial environments, such as large boulders and striations caused by the movement of ice. The formation of these deposits suggests that the Earth's climate was much cooler during this period, with ice sheets covering much of the planet. In contrast, during the Cretaceous period, which occurred around 100 million years ago, the Earth experienced a period of global warming that led to the deposition of limestone and chalk in areas outside the tropics. This is evidenced by the presence of extensive limestone deposits in places such as Europe and North America, which were located at mid to high latitudes at the time. These limestone deposits contain fossils of tropical organisms, such as corals and mollusks, which suggests that the Earth's climate was much warmer during this period. This warming trend is thought to have been driven by increased levels of atmospheric carbon dioxide, which acted as a greenhouse gas and trapped heat in the atmosphere. There is evidence for change in the climate of the British area caused by a change in its latitude, which is a result of the movement of tectonic plates over geological time. During the last 500 million years, the British area has moved from tropical latitudes to its current temperate latitude. The most obvious evidence for this change in climate is the presence of rocks and fossils that indicate different climate conditions. During the Devonian period, around 370 million years ago, the UK was located at around 30 degrees south of the equator. During this time, the area was dominated by arid deserts, which are reflected in the deposition of the Devonian red sandstones found in the UK. These sandstones show evidence of cross-bedding and other sedimentary structures that indicate wind deposition, which is typical of desert environments. Moving forward to the Carboniferous period, around 320 million years ago, the UK was situated near the equator. During this time, the area was covered by a shallow sea which supported a diverse range of marine life. The deposition of carbonates, such as limestone, is evidence of the existence of a warm tropical environment with clear, shallow waters that allowed sunlight to penetrate to the sea floor. This sea gave way to terrestrial conditions as deltas spread from the north, and by the end of the Carboniferous period, the British area was dominated by tropical plants preserved in coal swamps, further indicating its equatorial latitude, with the occasional return to marine conditions resulting from sea level change. During the Permian period, around 280 million years ago, the UK had moved to around 30 degrees north of the equator. During this time, the area was once again dominated by arid desert conditions, which are reflected in the deposition of red sandstones and evaporites. The deposition of evaporites such as gypsum and halite is evidence of a hot and dry environment with limited rainfall. Finally, during the Quaternary period, around 2 million years ago, the UK had moved to around 50 degrees north of the equator. This period is characterised by a series of ice ages, with the most recent ice age ending only around 10,000 years ago. Evidence of glaciation is seen in the deposition of boulder clay, which is a type of glacial till that is deposited by melting glaciers. The presence of erratic boulders, which are rocks that have been transported by glaciers and deposited in areas that are different from their source, is also evidence of glacial activity. There is evidence for changes in sea level throughout geological time, which have had a significant impact on Earth's surface and the organisms that inhabit it. One example of such evidence is the presence of drowned forests, which are ancient forests that have been preserved beneath the sea. Drowned forests are often found in coastal areas that were once above sea level but have since been submerged by rising sea levels. They are typically composed of tree stumps, roots, and other plant material that have been preserved by the sediment that accumulated over them after they were drowned by the rising sea. The age of these drowned forests can be determined through radiometric dating of the sediment layers that contain them. The presence of drowned forests provides evidence for changes in sea level over time. For example, during the last glacial period, around 20,000 years ago, sea levels were much lower than they are today, as a significant amount of water was locked up in glaciers and ice sheets. As the climate warmed and the ice sheets melted, sea levels rose, flooding coastal areas and drowning the forests that once grew there. Similarly, during warmer periods in Earth's history, such as the Eocene epoch around 56 to 33.9 million years ago, sea levels were much higher than they are today, due to a combination of factors, including tectonic activity and the melting of polar ice caps. Therefore, sea level changes can be caused by changes in the sea or land level, or a combination. Carbon dioxide is a greenhouse gas that plays a significant role in regulating the Earth's temperature and climate. There are various sources of carbon dioxide in the atmosphere, but two of the major contributors are volcanic emissions and the burning of fossil fuels. Volcanic emissions release carbon dioxide and other gases into the atmosphere during volcanic eruptions. These emissions can occur through vents, fumaroles, and volcanic plumes. While volcanic emissions contribute to the global carbon dioxide budget, they account for only a small fraction of the total amount of carbon dioxide released into the atmosphere each year. The burning of fossil fuels, such as coal, oil, and gas, is a much larger source of carbon dioxide in the atmosphere. Fossil fuels are the remains of ancient plants and animals that were buried and compressed over millions of years. When we burn these fuels for energy, carbon dioxide is released into the atmosphere as a byproduct of combustion. This process has increased dramatically since the Industrial Revolution, as the use of fossil fuels for energy production has become widespread. The accumulation of carbon dioxide in the atmosphere is a significant concern, as it contributes to global warming and climate change. The burning of fossil fuels is the primary cause of the increase in atmospheric carbon dioxide levels over the past century, and efforts to reduce carbon emissions and transition to renewable energy sources are critical to mitigating the impacts of climate change. There is evidence for changes in atmospheric carbon dioxide levels over geological time, which can be studied using ice cores and sedimentary rocks. Ice cores are cylindrical samples of ice taken from glaciers and ice caps in polar regions. The layers of ice in these cores represent the annual accumulation of snowfall and contain tiny bubbles of air from the time the snow was deposited. By analysing the composition of these air bubbles, scientists can estimate the atmospheric carbon dioxide levels at the time the snow was deposited. Ice cores have been used to study changes in atmospheric carbon dioxide levels over the past 800,000 years, revealing that carbon dioxide levels have fluctuated between approximately 180 and 280 parts per million during this time period. Sedimentary rocks, particularly limestone and dolomite, can also provide evidence of past atmospheric carbon dioxide levels. These rocks are formed from the accumulation of sediment on the ocean floor, and they often contain the remains of marine organisms such as shells and skeletons made of calcium carbonate. The formation of calcium carbonate involves the removal of carbon dioxide from the ocean and atmosphere, and the rate of carbonate deposition is thought to be closely linked to atmospheric carbon dioxide levels. By studying the abundance of different isotopes of carbon and oxygen in sedimentary rocks, scientists can estimate past atmospheric carbon dioxide levels. These studies have shown that carbon dioxide levels have been much higher in the past, reaching levels of over 1,000 parts per million during the Cretaceous period, approximately 100 million years ago. The carbon dioxide content of the atmosphere is subject to various feedback mechanisms, both positive and negative. Positive feedback occurs when a change in one component of a system leads to further changes that amplify the initial change. In the case of the carbon dioxide content of the atmosphere, one example of positive feedback is the reduction of ice cap albedo, accelerating warming. Albedo refers to the amount of sunlight reflected by a surface. When snow and ice melts, it reduces the surface's albedo, which means that more sunlight is absorbed and the surface heats up further. This can lead to the release of more carbon dioxide from the melting permafrost, which further amplifies the initial warming. On the other hand, negative feedback mechanisms work to stabilise the carbon dioxide content of the atmosphere. Negative feedback leads to decrease in temperatures and falling sea levels when carbon dioxide is dissolved in seawater and absorbed by organisms to form limestone. This process removes carbon dioxide from the atmosphere and sequesters it in the Earth's crust. The mechanism involves the chemical weathering of rock when atmospheric carbon dioxide is removed by rain to form carbonic acid. This results in the breakdown of silicate minerals and the release of carbonates into the ocean. In this way, carbon dioxide can be stored in marine sediments for long periods of time. Subduction and volcanic emissions can also affect the carbon dioxide content of the atmosphere. Subduction involves the sinking of one tectonic plate beneath another, which can carry carbonates down into the Earth's mantle, where they are eventually converted into carbon dioxide and released back into the atmosphere through volcanic eruptions. The balance between these feedback mechanisms determines the overall level of carbon dioxide in the atmosphere. Global warming and cooling can affect the size of continental ice sheets and the global sea level in the following ways. Number 1, global warming. As global temperatures rise, ice sheets on land begin to melt at a faster rate, resulting in a rise in global sea level. The warmer temperatures also cause glaciers to retreat and thin, which can contribute to sea level rise. Number 2, global cooling. As global temperatures decrease, ice sheets can begin to grow and expand, resulting in a drop in global sea level. This occurs because the colder temperatures cause increased snowfall and reduced melting rates, leading to the accumulation of more ice. The fluctuations in sea level due to changes in global temperature can have significant impacts on coastal regions and low-lying areas. Rise in sea levels can result in flooding and erosion of coastlines, displacement of populations, and damage to infrastructure. Conversely, fall in sea levels can cause coastal areas to become more exposed and vulnerable to erosion, as well as changes in marine ecosystems. Carbon sequestration, or capture, is a technique used to capture and store carbon dioxide from the atmosphere or from industrial processes to prevent it from returning to the atmosphere and contributing to global warming. One way to achieve carbon sequestration is by injecting carbon dioxide deep into the earth, where it can be stored in geological formations such as depleted oil and gas reservoirs, saline aquifers, or unminable coal seams. This process is called geological sequestration, or geologic carbon capture and storage, using the acronym CCS. In geological sequestration, carbon dioxide is compressed and transported to a suitable geological storage site, where it is injected into a deep underground rock formation. The carbon dioxide is stored in the pores of the rock, trapped by impermeable cap rocks above. Over time, the carbon dioxide dissolves in the formation fluids or reacts with the rock minerals to form stable carbonate minerals, making the storage permanent. Geological sequestration has the potential to reduce carbon dioxide emissions from fossil fuel-fired power plants and other industrial processes by up to 90%. However, it requires significant infrastructure and investment, and there are concerns about the potential for carbon dioxide leakage from storage sites and the long-term stability of the storage reservoirs. The origin and development of life on Earth. The origin of life on Earth is a topic of ongoing scientific research, and while the exact details are not yet fully understood, there is evidence to suggest that life likely originated in the oceans or hydrothermic pools around 3.5 billion years ago. One hypothesis is that simple organic molecules were formed in the early oceans through a series of chemical reactions, possibly driven by energy from lightning or UV radiation from the sun. These molecules then combine to form more complex organic molecules, such as amino acids, the building blocks of proteins. Another hypothesis is that life originated near hydrothermal vents on the ocean floor, where hot water and minerals are released from the Earth's crust. These environments provide a potential source of energy and a variety of chemical building blocks for the formation of organic molecules. In fact, modern hydrothermal vents, known as black smokers, have been found to support a diverse range of unique and adapted life forms, including bacteria and tube worms. The fossil record provides evidence for the development of diversity and the evolution of life over time. It shows the progression from the earliest single-celled organisms to the complex and diverse array of life we see today, including multicellular organisms, animals with hard parts, fish, amphibians, reptiles, mammals, birds, and humans. These evolutionary trends over time can be illustrated by simple evolutionary tree diagrams called cladograms. The fossil record documents major evolutionary events, such as the development of the first photosynthetic organisms around 3.5 billion years ago, the emergence of animals with hard parts during the Cambrian explosion about 540 million years ago, and the diversification of dinosaurs during the Mesozoic era. The fossil record also shows the evolution of hominids, including the emergence of the first human-like species around 2.8 million years ago, and the evolution of modern humans around 200,000 years ago. Through the analysis of fossils, scientists can observe changes in morphology, behaviour, and other traits that reflect evolutionary processes, such as natural selection, genetic drift, and speciation. By studying the fossil record, scientists can gain insights into the history of life on Earth and how it has changed over time. It must be remembered, however, that the fossil record is very much incomplete and is hugely biased in favour of marine organisms that had hard parts, mainly shells. Soft-bodied organisms and those that lived on land are poorly represented in the fossil record. Throughout Earth's history, there have been several periods where a significant number of species disappeared in a relatively short time. These events are known as mass extinctions, and they represent major turning points in the development of life on Earth. The most famous of these events is the Cretaceous-Paleogene mass extinction, which occurred about 66 million years ago and resulted in 70% of all life on Earth becoming extinct, including the dinosaurs and the ammonites. There are two main theories regarding the cause of this mass extinction, which are the meteorite impact theory and the flood basalt theory. Number 1, the meteorite impact theory proposes that the mass extinction was caused by a large asteroid or comet colliding with the Earth, which would have created a massive shockwave, triggered tsunamis, and caused widespread fires. The impact would also have thrown massive amounts of dust and debris into the atmosphere, which would have blocked out the sun's light and caused a global cooling effect, leading to a mass extinction of the majority of life on Earth. Evidence supporting this theory was discovered in the 1980s, when a layer of sediment containing high levels of iridium, a rare element found in asteroids and comets, was found all over the world, including in Mexico. This sediment layer is thought to have been created by the impact of a large asteroid or comet. Further supporting evidence comes from a 180-kilometre wide crater discovered at Chicxulub in the Gulf of Mexico for the correct age. Number 2, the flood basalt theory, proposes that the mass extinction was caused by a series of massive volcanic eruptions in what is now India. These eruptions would have released huge amounts of lava, ash, and gases, which would have caused global warming and acid rain. The global warming would have been caused by the release of large amounts of greenhouse gases, such as carbon dioxide and sulfur dioxide, into the atmosphere, which would have led to a warming of the Earth's surface and oceans. The acid rain would have been caused by the release of sulfur dioxide and other gases, which would have reacted with water vapour in the atmosphere, creating sulfuric acid. The evidence supporting this theory is the discovery of massive layers of volcanic rocks known as the Deccan Traps, which are thought to have been created by the massive volcanic eruptions in India. Both of these theories have evidence supporting them, but the most widely accepted theory is the meteorite impact theory, which is also known as the Alvarez hypothesis. The discovery of the iridium layer in sediment all over the world, as well as the discovery of a massive impact crater in Mexico, provides strong evidence for this theory. However, the flood basalt theory cannot be ruled out entirely, as there is still much debate among scientists regarding the cause of the KPG mass extinction. Indeed, it may be that the KPG extinction was not the result of one single cause. Mass extinctions are important because they create opportunities for new forms of life to evolve and diversify. For example, the KPG extinction paved the way for the evolution of mammals, which eventually led to the emergence of humans. Major fossil finds are an important source of information about the history of life on Earth. Here are a few examples of what we have learned from some of these finds. Rare and exceptional preservation. In some cases, fossils are preserved in such detail that even the soft parts of organisms remain, which provide a wealth of information about ancient life. One example is the Burgess Shale fauna, a collection of fossils from the Canadian Rockies that date back to the Cambrian period, around 500 million years ago. These fossils show a remarkable diversity of early animals, including many that have no living descendants. Unfortunately, marine organisms with shells are heavily overrepresented in the fossil record and is therefore biased. Links in macrofossil evolution. The discovery of Archaeopteryx, a bird-like dinosaur from the late Jurassic period, provided a key piece of evidence for the theory of evolution. Archaeopteryx had feathers, wings, and other bird-like features, but also had teeth and a long tail like a dinosaur. This combination of features suggested that birds evolved from small, feathered dinosaurs. Interpretation of incomplete remains. Fossil skeletons are often incomplete, and paleontologists must use their knowledge of anatomy and comparative anatomy to interpret what they represent. One example is the study of dinosaurs, many of which are known only from incomplete or disarticulated remains. By studying the bones that are present, paleontologists can learn about the size, shape, and behaviour of these ancient animals. Features of early hominids. Fossils of early human ancestors, such as Lucy, a 3.2 million-year-old Australopithecus afarensis specimen found in Ethiopia, provide important clues about the evolution of humans. These fossils show that early hominids were bipedal, but still had many ape-like features, such as a small brain size and long arms. Unfortunately, only a few quality specimens exist. Eduqas GCSE Geology. Topic 3. Planetary Geology. Planetary Geology. The Earth and its planetary neighbours, such as Mars and Venus, have both similarities and differences in terms of their geology and physical characteristics. The principle of uniformitarianism can be used to interpret the geological processes operating on planetary bodies within the solar system by comparing with those of Earth. Let's look at the similarities. All planets are solid, rocky bodies, except for gas giants like Jupiter and Saturn. They all have landscapes shaped by geological processes, such as impact cratering, volcanism, tectonism, and erosion. The planetary interiors are divided into layers with different compositions and properties. The surface rocks on the planets have similar mineralogical compositions. They all have atmospheres, although their composition and density vary greatly from planet to planet. They all have temperatures and pressures that change with altitude. And now the differences. The size and mass of the planets vary greatly, which affects their gravity and geology. For example, Mars has a lower gravity than Earth, which affects the height of its mountains. The planets have different atmospheres with different compositions and pressures. For example, Earth has a breathable atmosphere with a high concentration of oxygen, while Venus has a dense, toxic atmosphere of carbon dioxide. The planetary surfaces have different ages and histories of geological activity. For example, Mars has many ancient impact craters and extinct volcanoes, while Earth has a dynamic surface with ongoing tectonic activity and volcanic eruptions. The planets have different temperatures and environments, which affects the possibility of life. For example, Earth has a relatively narrow range of temperatures and abundant water, making it habitable for life as we know it, while Venus has a scorching hot surface with no liquid water, making it inhospitable for life. The Earth may currently be the only tectonically active planet in the solar system associated with plate tectonics. Other planets, e.g. Mars, being smaller than Earth, cooled quicker, but indicate surface evidence of past tectonic activity. The Earth is called the Goldilocks planet, as it is neither too hot nor too cold, and just the correct distance from the Sun for water to be able to exist in a liquid state. Being a rocky dense planet, it has a strong gravitational pull, which has helped it retain the dense atmosphere. The atmosphere protects from dangerous UV rays and also helps to moderate the temperature at the Earth's surface. The Earth's magnetic field deflects away charged particles from the solar wind. Meteorites are rocks that have fallen to Earth from space, and they can provide important clues about the composition of the Earth. The composition of meteorites is similar to that of the early solar system, and studying them can help us to understand the processes that formed the planets. There are three main types of meteorites: stony, iron, and stony iron. Stony meteorites, with a density of 3.6 grams per centimetre cubed, are mostly made up of silicate minerals rich in olivine, and are thought to be similar in composition to the upper mantle on Earth. Stony iron meteorites, with a density of 4.8 grams per centimetre cubed, are a combination of olivine, nickel, and iron, and are thought to be similar in composition to the Earth's lower mantle and outer core. Iron meteorites are made up mostly of iron and nickel, with small amounts of other elements, which are thought to be similar in composition to the Earth's inner core. Meteorites are rare and poorly preserved on Earth, but common and well preserved on the Moon and Mars. This is because on Earth, the atmosphere causes most meteorites to burn up before hitting the surface. Impacts from meteorites and comets may have had a significant effect on the evolution of the Earth and its biosphere, but the presence of oceans, surface processes, and plate tectonics often prevent meteorites or the evidence of their impacts being found or preserved. The internal structure of the Earth is quite different from other rocky and gaseous planetary bodies within the solar system, such as the Moon, Mars, and Jupiter. The Earth has a layered structure, consisting of an inner core, an outer core, the mantle, and the crust. The inner core is a solid sphere of iron and nickel, with temperatures reaching up to 5,500 degrees Celsius, while the outer core is liquid, also made of iron and nickel. The mantle is a thick layer of hot, solid rock that surrounds the core, and the crust is the thin outer layer of the Earth, made of solid rock. In contrast, the Moon has a relatively simple internal structure, consisting of a small iron core, a partially molten mantle, and a thin crust. Mars also has a layered structure, but its interior is not as well understood as the Earth's. It is thought to have a partially molten core, a mantle, and a thin crust, but there is still much to learn about its internal structure. Jupiter, on the other hand, is a gas giant and has a very different internal structure compared to the Earth. It has a small rocky core, but most of its interior is made up of a thick layer of metallic hydrogen, which is a form of hydrogen that behaves like a metal due to the intense pressure within Jupiter's interior. Above this layer is a layer of molecular hydrogen, and then an outer layer of atmosphere, made up of hydrogen, helium, and other gases. In summary, the internal structure of the Earth is unique among other rocky and gaseous planetary bodies within the solar system, with its layered structure consisting of an inner core, outer core, mantle, and crust. Geological processes that shape the Earth's landforms, such as erosion, weathering, tectonic activity, and volcanic eruptions, also occur on other planetary bodies within our solar system. By studying the landforms and geological features on other planets and moons, scientists can better understand the geological processes that shape them. Topographic highs and lows refer to the elevation differences on a planet's surface. Mountains are examples of topographic highs, while plains are examples of topographic lows. Volcanic shapes on other planetary bodies can vary greatly from those on Earth. For example, on the Moon and Mars, fissure and central vent volcanoes can be found. Fissure volcanoes are long cracks in the ground through which lava erupts, while central vent volcanoes have a single opening from which lava and other volcanic materials are erupted. The Martian central vent volcano of Olympus Mons, active 115 to 25 million years ago, is the largest volcano in the solar system, at 600 kilometers wide and 22 kilometers high. Much larger than any volcano on Earth. It developed because the heat magma source feeding the volcano remained fixed in place for millions of years as there were no plate movements. In addition, weak gravity allowed the structure to continue to grow. As there was no water on Mars by this time, the processes of weathering and erosion, except wind, did not wear it down. Additionally, calderas can form on the Moon and Mars as a result of volcanic activity. Calderas are large depressions in the ground that form when a volcanic cone collapses into its own magma chamber. Lava flows can also be found on other planetary bodies, such as the lunar Marias on the Moon. These are vast expanses of solidified lava that cover large areas of the Moon's surface. Canyons, channels, streams, and lake networks are also found on other planetary bodies. For example, Valles Marineris is on Mars, is a system of canyons that is over 4,000 kilometers long and up to 8 kilometers deep, and may represent the initial stage in the formation of a divergent plate boundary with a rift valley structure running along its center. Fault features, such as fault scarps, can also be found on other planetary bodies. These occur when there is movement along a fault line, causing the ground to crack and shift. Landslide features are also common on other planetary bodies, particularly on the Moon and Mars. These occur when loose rock and soil become unstable and slide down a slope. Meteorite craters can also be found on other planetary bodies, formed by the impact of meteorites hitting the surface. These craters can range in size from small impact pits to large multi-ring basins. Dunes have been identified on Mars, but are much larger than those on Earth, with some reaching up to 700 meters in height. The internal structure of these dunes show large-scale cross-bedding, dune bedding, exactly the same as those on Earth. The dunes are interpreted as being formed by sand blown in a series of mega-ripples by a unidirectional current. Sand dunes cover large areas on Mars as there is an absence of moisture and vegetation to anchor the sand. Glacial features, such as those found on Mars, are caused by the movement of ice across the planet's surface. These features can include valleys, ridges, and other formations created by the movement of ice. Planetary landforms can provide evidence for unseen Earth processes in a few ways. One example is the study of moon impact craters. By analysing the size, shape, and distribution of these craters on the moon's surface, scientists can learn more about the history of impacts on the moon, as well as the impact history of the inner solar system, including Earth. Some planetary bodies like the Moon and Mars have a large number of well-preserved impact craters because they lack significant tectonic activity and atmospheric erosion. Studying moon impact craters has helped scientists understand the frequency and size distribution of asteroid impacts on Earth throughout its history. Generally, the larger the meteorite craters, the older they are. More recent ones are smaller. Cross-cutting relationships of overlapping craters can be used to establish their relative ages. This information is important for understanding the potential risks and hazards associated with asteroid impacts on Earth today, and for developing strategies to mitigate those risks. Additionally, the study of planetary landforms can provide insights into geological processes that occur on Earth but are difficult to observe or study directly. For example, the study of Mars's surface features, such as channels and valley networks, has helped scientists understand the role of liquid water in shaping planetary surfaces. This information can also help inform our understanding of how water and other geological processes may have shaped the Earth's surface over time. Meteorite impacts have played a significant role in the evolution of Earth and its biosphere over geological time. Large impacts can cause mass extinctions and changes to the environment that can have long-lasting effects. The collision theory of the Moon's formation suggests that the Moon formed out of the debris left over from a collision between Earth and a Mars-sized planetesimal approximately 4.5 billion years ago. According to this theory, the impactor struck the Earth with a glancing blow, ejecting a large amount of debris into space. This debris eventually coalesced to form the Moon. The Moon has a significant influence on tides because of its gravitational pull on the Earth's oceans. As the Moon orbits the Earth, its gravitational force causes the oceans to bulge outward on the side of the Earth, facing the Moon, creating high tides. On the opposite side of the Earth, the gravitational force is weaker, causing a second high tide. This creates a cycle of 2 high tides and 2 low tides each day. The Moon's gravitational influence on the Earth also affects the planet's rotation. As the Moon pulls on the Earth's oceans, it creates a drag that slows down the rotation of the planet. Over time, this has caused the length of an Earth day to increase. It is estimated that the Earth's day was approximately 6 hours long at the time of the Moon's formation, and has since increased to its current length of approximately 24 hours. The origin of life on Earth may be linked to the early bombardment of the Earth by comets and meteorites around 3.85 billion years ago. These impacts could have delivered water and organic molecules to the Earth, providing the building blocks necessary for life to emerge. Additionally, some scientists believe that the heat generated by these impacts could have created hydrothermal vents on the ocean floor, which could have provided an ideal environment for the first life forms to develop. Large meteorites and comets have the potential to significantly impact Earth's climate and biosphere. In the short term, impacts can cause wildfires, tsunamis, and global cooling, which can disrupt the biosphere and lead to mass extinctions. For example, the impact that caused the KPG mass extinction 65 million years ago is believed to have triggered a global cooling event that led to the extinction of the dinosaurs. In the long term, impacts can also cause global warming, which can also lead to extinctions. Overall, large impacts have played an important role in shaping the Earth's history and the evolution of life on the planet. Eduqas GCSE Geology. Topic 4. Human interaction with Earth. Earth hazards and their mitigation. Geological events can pose hazards to human populations and infrastructure. Here are some examples. Earthquakes. These mainly occur when two tectonic plates move against each other, releasing energy that causes the ground to shake. The shaking can cause damage to buildings and infrastructure, and can trigger landslides or liquefaction, which can be further hazards. Earthquakes are recorded and measured using seismometers, which are instruments that detect and record ground vibrations caused by seismic waves. The two most commonly used scales to measure earthquakes are the Modified Mercalli Intensity Scale and the Moment Magnitude Scale. The Modified Mercalli Intensity Scale is based on the observed effects of an earthquake on people, structures, and the natural environment. It ranges from 1 to 12, with 1 being imperceptible and 12 representing complete destruction. The scale is subjective and varies depending on the location of the observer. For example, an earthquake with an intensity of 7 in a rural area may have a different impact than the same intensity earthquake in a densely populated city. The moment magnitude scale, on the other hand, measures the amount of energy released by an earthquake at its source, also known as its magnitude. The scale is logarithmic, meaning that a magnitude 6 earthquake represents 10 times the amplitude of a magnitude 5 earthquake, and 100 times that of a magnitude 4 earthquake. The scale has no upper limit, but earthquakes of a magnitude of 9 or greater are extremely rare. Both scales provide useful information about the strength and impact of an earthquake, and scientists often use them in combination to better understand the seismic activity in a region. Next, let's look at volcanic eruptions. Volcanoes release lava, ash, pyroclastic flows, which are hot gases and ash, and mud flows. These can destroy homes, vegetation, and infrastructure, and can cause respiratory problems for people and animals in the area. Volcanic eruptions can also cause climate change, as the ash and gases released into the atmosphere can block sunlight and cause cooling. The type of volcanic hazard associated with a volcano can be linked to the type of magma that the volcano erupts. Basaltic magma is relatively low in viscosity, which means it is thin and flows easily. As a result, basaltic eruptions are typically not very explosive and do not produce significant ash or pyroclastic flows. However, basaltic eruptions still pose a hazard from lava flows, which can destroy property and infrastructure in their path. Andesitic magma is more viscous than basaltic magma, which means it is thicker and flows less easily. As a result, andesitic eruptions are typically more explosive than basaltic eruptions and can produce significant ash and pyroclastic flows. During heavy rainfall, these materials often produce lahars, which are mud flows composed of volcanic debris and water that can travel long distances and cause significant damage. In summary, basaltic volcanoes tend to produce lava flows as their primary hazard, while andesitic volcanoes are more likely to produce explosive eruptions, ash, pyroclastic flows, and lahars. Another hazard is landslides. These occur when slopes become unstable and rocks, soil, or debris slide downhill. Landslides can be triggered by heavy rain, earthquakes, or other factors. They can be dangerous to people and infrastructure downhill and could cause subsidence in the area. The next hazard is tsunamis. These are giant waves that are secondary hazards, usually triggered by earthquakes or volcanic eruptions under the ocean. They can cause widespread damage to coastal areas, flood in homes and infrastructure, and can cause loss of life. It is important for people in areas that are prone to geological hazards to be prepared, with emergency plans and supplies on hand. Scientists also study geological hazards to better understand their causes and potential impacts, and to develop early warning systems that can help save lives. Geological hazards pose a risk to life and property, and the level of risk is associated with several factors. Population density is one of the most critical factors. Areas with a high population density are more vulnerable to the effects of a geological hazard. For example, an earthquake that strikes a densely populated area is likely to cause more casualties and property damage than one that occurs in a sparsely populated region. Technology and building standards also play a role in the level of risk posed by a geological hazard. Buildings that are designed to withstand seismic activity are less likely to collapse during an earthquake. Areas with better building codes and infrastructure are also more likely to recover quickly from a geological hazard. Development factors such as economic situation, education and communication also play a role. For example, areas with higher levels of poverty may lack the resources and infrastructure necessary to prepare for and respond to a geological hazard. In contrast, areas with better education and communication systems may be better equipped to understand the risks of geological hazards and take steps to reduce their impact. Hazard prediction is an important aspect of mitigating the impact of geological events on human life and property. However, predicting geological hazards with a high level of accuracy is challenging because the processes that lead to these hazards are often complex and influenced by a range of factors. Additionally, data and monitoring tools are not always available or sufficient to provide accurate predictions. For example, earthquakes can't be predicted as they occur due to the movement of tectonic plates, which are deep beneath the Earth's surface. Seismologists can use various methods to detect and monitor seismic activity, but predicting the precise timing and magnitude of an earthquake is still a significant challenge. At best, scientists can only calculate the probability that a significant earthquake will occur in a specific area within a certain number of years. Similarly, predicting volcanic eruptions, although more reliable, can be complex as it depends on the behaviour of the magma within the volcano. Seismologists, geologists, and volcanologists use a range of techniques to monitor volcanoes, including seismic activity, ground deformation, and gas emissions. However, even with these monitoring tools, predicting the timing and size of an eruption remains challenging. In summary, while scientists and researchers have made significant progress in hazard prediction, there are still limitations to the level of accuracy that can be achieved. Reducing the risk of geological hazards is crucial to minimise their impact on life and property. Some of the methods to reduce the risk of geological hazards include building design and regulation, hazard prediction, warning schemes, and evacuation. Building design and regulation can help to reduce the risk of geological hazards by ensuring that structures are built to withstand potential hazards, such as earthquakes or landslides. Building codes can specify requirements for construction materials and techniques that make structures more resilient to natural disasters. Prediction of geological hazards is also an essential tool to reduce risk. Scientists can use various methods to predict hazards, including monitoring patterns of seismic activity, ground deformation, groundwater changes, and gas emissions. For example, seismologists may look for seismic gaps, areas where an earthquake has not occurred for an extended period, in order to forecast where the next earthquake may occur. Warning schemes and evacuation plans are also vital to reduce the risk of geological hazards. By providing timely warnings to communities at risk, individuals can take steps to protect themselves, evacuate if necessary, and reduce the impact of the hazard. Despite these methods, the level of accuracy of hazard prediction is limited. Geological hazards can be complex and unpredictable, making it difficult to forecast the exact timing and impact of an event. Therefore, it is essential to have emergency response plans in place and to educate communities on the potential hazards and ways to prepare for them. Next, let's look at Earth resources and engineering. Resources are naturally occurring materials or substances that have potential economic value, including minerals, metals, oil, natural gas, coal, and water. These resources can be found in rocks, sediments, and soils, and are extracted for a variety of purposes, such as energy production, construction, and manufacturing. Reserves, on the other hand, are the estimated quantities of a resource that can be economically extracted using current technology and under current economic conditions. Reserves are a subset of resources and are based on a range of factors, including the quality and quantity of the resource, the cost of extraction, and the demand for the resource. It is important to distinguish between resources and reserves, because not all resources are economic to extract. A resource may be plentiful in a particular area, but if it is difficult or expensive to extract, it may not be considered a reserve. Additionally, changes in technology or economic conditions may affect the viability of reserves over time. Mineral resources are essential for various industries, including construction, industrial manufacturing, and energy generation. Minerals like quartz, feldspar, and mica are used in the manufacturing of glass, ceramics, and electronics. Metals like iron, copper, and aluminium are essential for construction, machinery, and transportation. Minerals like coal, oil, and natural gas are the primary sources of energy for the world. In our modern technological world, critical minerals such as lithium, nickel, cobalt, and rare earth elements are indispensable components in our rapidly growing clean energy technologies, including wind turbine and electric vehicles, and are essential for our communication systems, such as mobile phones and computers. Limestone is a sedimentary rock composed mainly of calcium carbonate. Its physical properties, such as hardness and durability, make it a suitable material for aggregate and construction. Crushed limestone is used as a base for roads, as a filler in concrete, and as a material for building and paving. Hematite, also known as iron oxide, is a mineral that is the primary source of iron used in the steel industry. Its physical properties, such as its high density and hardness, make it an ideal material for making steel. Hematite is mined and processed to extract iron, which is then used to make steel, an essential material for construction, transportation, and infrastructure. Uranium is a naturally occurring radioactive element that has been used as a fuel in nuclear power plants. Its physical and chemical properties make it an excellent fuel for nuclear energy. Uranium has a high energy density and releases a large amount of energy when its atoms split, a process known as nuclear fission. However, uranium is also highly radioactive and requires careful handling and disposal to prevent environmental and health hazards. Without mineral resources, modern life would be impossible. However, it is essential to use them sustainably, as many are non-renewable and finite in quantity. Therefore, it is crucial to identify and conserve mineral resources for future generations, while ensuring that extraction and use do not harm the environment. Geologists use various techniques to prospect for new reserves of minerals, oil and gas. These techniques include, number 1, geological mapping. This involves studying the surface geology of an area to identify rocks and minerals that are likely to contain valuable resources. Geologists study the age, composition, and structure of rocks and map the distribution of minerals on the surface. Secondly, borehole correlation. This technique involves drilling boreholes into the earth and collecting samples of rock and sediment. The geologists then use microfossils in these samples to identify the age and correlation of the rock layers. Number 3, geophysical methods. Geophysical techniques include seismic surveys, magnetic surveys, and ground-penetrating radar. Seismic surveys involve creating shock waves and measuring the time it takes for them to reflect off underground rock formations. Magnetic surveys measure variations in the Earth's magnetic field caused by different rock types, while ground-penetrating radar uses radar waves to penetrate the ground and detect changes in the subsurface. Number 4, geochemical methods. Geochemical methods involve analysing soil and river sediment samples to detect the presence of minerals and elements that may indicate the presence of valuable resources. Oil and gas resources are found in rocks that have been buried and subjected to heat and pressure, leading to the formation of hydrocarbons. The following are the characteristic structures and rock properties associated with the migration and accumulation of oil and gas in potential onshore and offshore gas or oil field resources. Number 1, source rock. This is the rock where the hydrocarbons are formed from organic matter such as algae and plankton. It is usually fine-grained, sedimentary rocks, like shale. Number 2, reservoir rock. This is a porous and permeable rock that acts as a storage space for oil and gas. The reservoir rock is usually a sandstone, limestone, or a fractured shale. Number 3, cap rock. This is an impermeable rock that overlays the reservoir rock, preventing the oil and gas from escaping. The cap rock is usually a rock like shale, mudstone, clay, or rock salt. Number 4, trap. Traps are geological structures that allow oil and gas to accumulate. The following are the main types of traps. Anticline trap. This is a fold in the rock layers that forms a dome-like structure. The reservoir rock is in the crest of the fold and is covered by a cap rock. Fault trap. This is a fracture in the rock layers that allows the reservoir rock to move upward and be covered by the cap rock. Unconformity trap. This is a type of trap where the reservoir rock is eroded and overlaid by a cap rock. Finally, salt dome trap. This is a trap where salt domes have pushed up through the rock layers, creating a trap for oil and gas. Exploring for and extracting oil and natural gas can involve various technological difficulties and environmental issues. One of the technological difficulties is that oil and gas reserves can be in remote or difficult to reach locations, such as deep offshore areas, the Arctic, or shale rock formations. This can increase the cost and complexity of exploration and production, as specialised equipment and techniques are often required. Some oil and gas reserves are unconventional, meaning they require more complex methods of extraction. For example, shale gas is often extracted using hydraulic fracturing or fracking, which involves injecting water, sand, and chemicals into the rock to release the gas. However, fracking has been controversial due to concerns about its potential environmental impact, such as contamination of groundwater and air pollution. Environmental issues associated with oil and gas exploration and production include land and habitat disruption, pollution of air and water, and greenhouse gas emissions. For example, drilling can cause soil erosion and fragmentation of wildlife habitats, while oil spills from offshore rigs can harm marine life and damage coastlines. In addition, burning fossil fuels such as oil and gas releases carbon dioxide and other greenhouse gases into the atmosphere, contributing to global climate change. This has led to efforts to reduce the use of fossil fuels and transition to renewable energy sources. Groundwater is an important resource for human consumption, agriculture, and industry. Aquifers are underground layers of permeable rock, sand, or gravel that hold and transmit water. The extraction of underground water from aquifers depends on several factors, including: firstly, the height of the water table. The water table is the upper surface of the saturated zone in the ground. It can be high or low, depending on the amount of rainfall, the permeability of the soil, and the rate of recharge, so the amount of water added to the aquifer. When the water table is high, it is easier to extract water from wells, but it can also cause flooding. Secondly, porosity and permeability of the aquifer. Porosity is the percentage of void space in a rock or sediment, and permeability is the ability of a rock to transmit water. The higher the porosity and permeability of the aquifer, the easier it is to extract water. Thirdly, the presence of natural springs. Springs are places where groundwater flows out of the ground to the surface naturally. They are a visible indication of the presence of an aquifer and can be used to extract water. Fourth, the distribution of wells. Wells are holes drilled into the ground to extract water. The location and number of wells are important factors in the extraction of groundwater. Wells should be placed in areas with high water availability and away from contamination sources. However, excessive extraction of groundwater can cause the water table to drop, leading to a decrease in water availability and the formation of sinkholes. In coastal areas, over-extraction risks saline water being drawn in to contaminate the aquifer with salt. Therefore, it's important to manage the extraction of groundwater sustainably and to avoid over-pumping. The impact of waste disposal on aquifers depends on several factors. One important factor is the permeability of the rock or sediment that makes up the aquifer. If the rock is highly permeable, a plume of pollutants can easily move through it and contaminate the water in the aquifer. Engineering factors can also play a role in protecting aquifers from contamination. For example, geomembranes must be used to line waste disposal sites and prevent pollutants from leaching into the ground. Another important factor is monitoring of potentially polluted water. It is important to regularly test the water in an aquifer to ensure that it is safe to drink. If pollution is detected, steps can be taken to identify the source of the pollution and prevent further contamination. If an aquifer does become contaminated, restoration of the contaminated ground may be necessary. This can involve removing contaminated soil or sediment, treating the water in the aquifer to remove pollutants, or even capping the contaminated area to prevent further contamination. Alternative techniques involve using microbes and/or plants to extract the toxic materials from the ground. These can then be removed or harvested and treated so that they are safe. Toxic waste can be stored in sealed drums, either underground in impermeable rocks, such as in disused salt mines, or at the surface in secure repositories. Overall, it is important to be mindful of the impact of waste disposal on aquifers and take steps to protect these valuable resources. Geological factors play a crucial role in determining the location and feasibility of engineering projects, such as reservoirs, dams, tunnels, and cuttings. The permeability, stability of bedrock, dip of strata, and the presence of faults and joints are all important factors that must be considered. Permeability refers to the ability of rock or sediment to allow water or other fluids to flow through it. When constructing a reservoir or dam, for example, it is important to choose a location where the surrounding bedrock is impermeable, so that the water held in the reservoir or behind the dam does not seep away. Similarly, when digging a tunnel or cutting, it is important to choose a location where the bedrock is not too permeable, as this can lead to stability issues. The stability of bedrock is another important factor to consider. A stable bedrock is necessary to ensure the safety and longevity of any engineering project. The presence of unstable geological formations, such as fault zones, weak rocks, or landslides, can increase the risk of failure of the project. The dip of strata refers to the angle at which rock layers, or strata, are inclined relative to the horizontal plane. The dip can affect the stability of slopes and the flow of groundwater. This will result in expensive slope stabilisation methods being needed. Locations where strata dip away from the excavations are naturally stable. It is important to consider the dip of strata when constructing a dam or reservoir, as it can affect the volume of water that can be held. The presence of faults and joints is also an important factor to consider. Faults and joints can create weak points in the rock that may be prone to failure or erosion. Fault reactivation may also occur, and expensive engineering solutions will be needed to make these areas stable. When constructing a tunnel or cutting, for example, it is important to consider the presence of faults and joints and to take measures to stabilise them. Overall, a thorough understanding of the geological factors involved is crucial when siting engineering projects to ensure their safety and long-term viability.
Ouch! This is why in some videos I explain scratches.